Hello, Sarah.
Hi, how are you doing?
Hi.
Good, how are you?
I'm good. I'm happy it's Friday.
So I just started the live, okay?
Okay. Sounds good.
Hello, Sarah.
Hi, how are you doing?
Hi.
Did y'all just hear ourselves reflected back?
Yeah, that's that's
I was
why.
like, that sounds remarkably like my voice. Who else heard that?
No, because I was like just logging to the YouTube channel, check that it's working, and
There's
yeah.
a small lag, is it?
Yeah, but wait, actually last time because there shouldn't be lag. Last time I changed it, like following the instruction from Dan. I changed it and I tested it, and now it still seems to be a lag, which is strange. Yeah, there's a lot of lag. Okay, I need to check that next time. Not sure why it's happening. So let's wait maybe like 2 more minutes, and then you can go, Nandita.
Sure. Should I start sharing my screen right now?
Yeah, sure. You can start sharing your screen.
Or you can show all our faces for some more time.
Yeah, I mean, it's fine. You can share when you want. Unless someone really wants to have their face recorded a bit longer. So I saw like on the mailing list, they are not, I don't know if like, I don't see that there was a lot of activity on Slack, and on the mailing list, there are not like as many people as came to the original meeting. So yeah, I don't know if people are just not getting the info.
I'm not sure. I mean, I think everybody has the schedule from the original email list, so
Yeah.
Probably just whoever is interested. I did put out on Chris's Slack this morning. So
Okay. Okay. Yeah, and also before we go to the presentation, there was Minaj from Dennis Group who asked me like there's someone, yes, some colleagues that are outside of Stanford would like to join, and I told him, yeah, they can ask the question in the on the live streaming, but you know, then they cannot go to the next. They won't be able to follow the next 30 minutes. So yeah, I don't know what's our like policy on that. We didn't discuss it yet, so I don't know what you think. They can join like the Zoom meeting even if it's not Stanford affiliate.
I think that's okay. You can just share the Zoom link.
Okay. Okay, then I will take it.
Sounds good. Thanks.
Yeah. Okay, so you audit. I don't need to tell you. Okay, so when you want, Nandita.
Oh, okay. I can get started then.
Yeah.
Do you guys see my presentation mode?
Yeah, I can see it.
Okay, great. So hi everyone. For those who don't know me, I'm Nandita Bhaskar. I'm a PhD student in Daniel Rubin's lab, and today for our reading group, I've picked a very recent paper from Google Research. So it's called Scaling Up Visual and Vision Language Representation Learning with Noisy Text Supervision. So before I go into the meat of the presentation, I want to show some cool things from this paper. So it's called Align. So it's a large scale image and noisy text embedding. And you can make text queries and then retrieve images. And the results are pretty cool. At least what they've shown in the paper. I don't know if it's cherry picked or not. But if you type in Van Gogh Starry Night, it gives you different images based on what details you specify. So if you say Van Gogh Starry Night in black and white, it actually gets you the black and white image, and versus a canvas or in a dark wood frame and so on. And just to give a few more examples, so Lombard Street, which is a street in San Francisco. So the bird's eye view actually gets the bird's eye view. And I don't know what it says in heavy rain, but I think it's the right one. So, and again, this I thought was also pretty cool. A seagull in front of Golden Gate Bridge versus London Tower Bridge, Sydney Harbour Bridge, and so on. The other interesting application for this is you can actually give image and text queries and retrieve a corresponding image. So for instance, you can provide this image of a pair of shoes and then say, I want it with beige, and then it gets the corresponding image in that color. And you can specify this butterfly picture and then say without the flowers, and then it gets you the corresponding picture. So these are some of the cool applications for this. But oh, there's one more, I guess. Yeah, and I was particularly impressed by the penguin example because penguin plus forest actually gave an answer which I was surprised, but it was pretty good in the waterfall minus the bridge, minus the waterfall, and minus the mountain. So that was nice. So let's jump into what is this paper about, what's the motivation behind it, and how they've actually implemented this. So the what is just, we want to learn pre-trained representations for both vision as well as vision language. And there's been a lot of interest in the recent past. This is one of the papers from a group of papers for learning visual representations from text to textual supervision. So there have been other famous papers right before this as well, but this is the most recent one. And coming to the why, vision applications typically use large-scale data sets with explicit class labels, and more often than not, it's supervised training, and people are trying to move on beyond the realm of supervised training with self-supervised or weak supervision and so on. And vision language applications, one of the biggest bottlenecks is that they have data sources that require a lot of manual work. So you spend a lot of time cleaning the data, balancing all the classes, performing a lot of human annotations, and along with semantic parsing and so on. So obviously, these things are really hard to do, especially on a scale of a huge data set. This is immensely taxing. So the aim is to actually do all this in a simpler way, but still get the same performance. So how does Align actually do it? So they use large scale data, which is 1 billion image text pairs. So just to give a context, I think ImageNet and other things have around the order of millions, whereas this actually uses 1 billion. And I think the largest text image data has on the around the order of 10 million data samples. And how do we actually get these billion image text pairs? They don't ensure that the data is very clean, so they leverage just very simple data with very little filtering, and so it's incredibly noisy. But because of the huge scale, they're able to get the required results. And because it's a language and image representations that we are trying to learn, we want shared embeddings. So they use a simple dual encoder architecture using the contrastive loss method. So in another word, to give an analogy, like these pad texts can act as fine-grained labels for the images. And you can think of the text encoder actually generating the label weights instead of the label weights being available as ground truth. So the dataset curation is something that sets a line apart from previous approaches. So they follow the same protocol as the conceptual captions dataset. So the main point is they scrape web images and then get the corresponding alt text pairs that's embedded in the HTML tags. So that's a very easy way of pairing images and text. And you have to note that they do no heavy filtering or processing. So it is going to be very noisy, but at the same time, because you're not filtering out a lot of examples, you have a very large data set, and precisely it's 1.8 billion pairs. And so let's take a look at what these image-based filtering methods are. So they remove all unsuitable or restricted images. They have some heuristics like keep images with aspect ratio less than 3, make sure that the shortest dimension has at least 200 pixels, and then discard images with more than 1,000 alt text. I'm not exactly sure when this scenario will arise. So that's, but anyway, they do this pre-processing step. And they also remove duplicates of test images in downstream tasks. So they don't use any of the images that they have in the test data sets, and then just so that there's no repeats. And then they also do a text-based filtering. So they remove, because it's the alt text in the HTML tags, they are quite noisy. So they remove all these that are shared by more than 10 images. Usually it's often something like something completely irrelevant. So, and then they also remove these texts with rare tokens, and they define rare as being outside of 100 million most frequent tokens in the raw data. And they also remove texts that are too short or too long, less than, so they want a range between 3 and 20 unigrams. So the framework, the actual framework for this paper is actually very similar, and we've seen this architecture before in Convert, which is interestingly contrastive learning for medical visual representation in particular. Usually I find the trend is always people come up with lots of models for natural images, and then the medical community starts to use it. But this trend was actually the reverse, where the medical community came up with this architecture before it's used for natural images. So you have the noisy text and image data, and then you have two separate encoders, one for an image, one for the images and one for the text. And then you try to push those, push all the embeddings of the positive samples together and push the negative samples embeddings away from each other using a typical contrastive learning approach. And they use the cosine similarity training laws. And for the image encoder, they use this efficient net L2 with global pooling. And I was kind of curious because their data set should be very noisy with all sizes and shapes of images, like how they actually find a size for an image that goes really well into that encoder. But they said that they've chosen 346 by 346 input. So they resize all inputs to that dimension and then get a final resolution of 289 cross 289. And then they do random crops and horizontal flips during training and a central crop during evaluation. So apart from these details, other details are kind of missing because the paper doesn't really have an appendix section. So I think it's still under progress. And for the text encoder, they use a large BERT with class tokens embedding and a fully connected layer in the end, just to ensure that the text representations and the image representations have the same size. And just for the sake of comparison, Convert uses rest nets instead of efficient nets. So they've moved away from rest nets in Align as well. I think the most important part of this framework is the loss function. So it's again the same as convert. And so if you remember the simpler presentation from last week, it follows the same softmax loss for contrastive representations. So you have the positive samples in the numerator and then all the other negative examples in the denominator. And because we are having multimodalities, there is image to text as well as text to image loss. And then the final loss is just a combination of both of them. And in this case, X and Y are the normalized representations from the image and the text encoder. So that's why they've written X transpose Y. But in reality, it's actually just the cosine similarity if you do not do the normalization. And I think that so as we all know, contrastive learning highly is dependent on the number of negative samples. So in this case, the way they get their positive samples is all the image and text pairs that are together, and negative samples are all other random image and text pairs. So this means that the negatives can be noisy, but because they have 1 billion images, it probably doesn't matter, and it can be overcome. So this one trick I thought was pretty cool. They concatenate embeddings from all computing cores to form a larger batch. So they use 1024 TPU cores, but then they use only 16 positives on each core. But effectively, their batch size becomes around the order of 16,000, which ensures that you have a really good set of negative samples. And if you have any questions, feel free to stop me and ask. And then moving on to how they evaluate their framework, they have a stream of downstream tasks. So the first few data sets that they use are the Flickr 30K and the MSCOCO. So they focus on image to text retrieval as well as text to image retrieval, both with and without fine tuning. So that is zero-shot learning. And then they use the crisscross captions dataset, which is actually pretty cool because it gives a lot of semantic annotations. I think it has been curated well enough that all these possible retrieval options are available. So you have image to text, text to image to image, and text to text. So you have both intermodal and intramodal, as well as evaluate semantic textual similarity, as well as semantic image similarity and image text similarity. And apart from that, they do purely image classification tasks as well. So they just use the image encoders pre-trained version and then perform downstream tasks and then evaluate the performance. So obviously ImageNet, they use the ImageNet benchmark with a frozen encoder and a fine-tuned classification layer, as well as a fully fine-tuned classification layer. A fully fine-tuned encoder. And they have a lot of other small data sets for image classification as well. So coming to the results, the bottom line is when it comes to the image and text tasks, Align outperforms all other methods for both zero-shot as well as fine-tuned settings, as well as all the intermodal retrieval tasks. And Clip, which is another method I'll talk about, which is their main competitor, is pretty close, but maybe slightly behind. And they use this metric called recall at K, which used to be common for retrieval. So it's the number of it's the percentage of ground truths in the queries when it the number of queries which contains the ground truth in the top K retrievals, and then they vary K from 1, 5, and 10. And an interesting feature that they point out is that Align is actually not very good at intramodal tasks. So anything that's text, or image, or if you want to measure textual similarity or image similarity. And one of the possible hypotheses is that because Align is focused on cross-modal matching rather than intramodal matching. And one suggestion that people give is maybe if you do a multitask setting for this approach where you focus on both cross-modal as well as intramodal, maybe we can get more balanced representations that actually capture the semantic meaning better.
Question?
Oh, yeah, sure.
Yeah, so because in the loss, it's only like text to image and image to text. There is no term that accounts for text, image, right?
Exactly.
Yeah, so there's nothing that forces it to be good there. Yeah, okay.
True. But I think the hypothesis is that if it's learning really good representations and if it's performing really well on these tasks, you expect it to be reasonably well, perform reasonably well even for intramodal tasks, even though the loss doesn't explicitly encode it.
Yeah, true. Do they report some results on that, or they just discuss it and say that it doesn't work well?
No, so they've actually reported all. So they have like a bunch of 5 tables. I just didn't put it in the slides because it came later. But yeah, they do report all the performance for the intramodal tasks as well. And then other baselines are like most of them are better than Align or equally performing. So
okay, thank you.
Yeah, and in the image only tasks, I think the main takeaway is that it's reasonable enough. Like the table has like some benchmarks it does really well, some it doesn't do well at all. So I think I don't know if Align is good enough as a standalone image encoder. So it's just reasonable in my opinion. But if you want to take a look at the actual values for each of the data sets, you should take a look at the paper as well. And they performed 2 main ablation studies. One is the effect of the model architecture size on performance. And so the unsurprising bottom line is that bigger is better. So both the text and the image encoder, they found that the larger number of parameters model always outperformed the one with lesser number of parameters.
So how many parameters is mini?
I actually don't know, but I'm still pretty sure it's big enough.
Million.
Yeah. And the other ablation study that they perform is on training data size. And again, the bottom line is the more training data you have here is better, because they tried it with 3 different situations, one with the entire data set, one with just 10% of the data set, and one with just the 3 million points in the highly curated data set. And they found that only if you use the full data set do you actually get the required performance. So if you choose only 3 million data points, the performance drops to like over 20 points, which is quite drastic.
That's actually not as big of a gap as I would have expected from a 10x increase in data, right? Like the
oh, you mean you said 10% versus
yeah,
the full?
from the 10% to the full, like
my reaction as well.
But I think it's 1 billion parameters, so 10% of that is still quite large compared to the millions that people typically work with. But I think after a certain point, it kind of, I think there's a sweet spot where like below that, the lesser number of data you have is actually hurts your performance more. But I don't think they've done more studies on this yet. But it is true that a 10% difference gives only 1 point reduction.
mm-hmm. Yeah.
And so one thing that I think we need to address is we had a similar model come out from OpenAI very recently. So it also has pretty cool applications. So it's the contrastive language image pre-training model from OpenAI. It's again also contrastive, also image text, except that it uses different encoders. So for the vision encoder, they use a vision transformer, and then for the language encoder, they use the GPT family. And I thought it was also good to compare the training times. I think both of them are pretty huge. They are 256 GPUs for 2 weeks. And the authors of Align claim that the dataset curation for CLIP is complicated because they need to first construct high frequency visual concepts from English Wikipedia, which involves a fair amount of curation. So I think one of the biggest selling points for Align is that they do minimal pre-processing, yet have the same performance or outperform CLIP.
What was the training time for Align?
So Align, they didn't mention training times, but the number of cores that they use is like 1024 TPU cores. So they don't actually give a time. Yeah. And so just some of the takeaways from Align are, okay, it gives pretty cool performance on image text retrievals, especially for natural image on the web. And if you have a large enough scale, then you can compensate for the noise. So you can go easy on the filtering, and then you don't need to curate it as much. In that context, methods might not be as useful for medical data because it's hard to get such large scale data sets just by scraping the web. But this dual encoder architecture is useful and has been shown to be useful by Convert. So that's something that we can use. And of course, you need a lot of compute, especially if you have data on the order of 1 billion. And as I was reading this paper, I think I would have liked to see some of these things, but I didn't see this in the paper. I would have liked results reported on metrics other than recall at K, because I think just that metric alone is not sufficient. So I think they might have reported precision at K or other metrics as well. And one thing that I was curious about is the shift from rest nets to dense nets to efficient nets. They did a pretty good ablation study on varying the number of parameters of efficient nets, but then I think it might be useful to also study this change in model architecture for contrastive loss as well. And I think the technical details about the dataset curation and model implementation were a little lacking because there was no appendix section as of now. And I think the biggest contribution is not really the dual encoder, but rather how they managed to get such a large data set without any noise, and then with a lot of noise and still implement it. So I think that's still, they're probably still working on it. And I would have liked to see a better related work section, despite the fact that their framework is fully based on Convert, there's not enough credit given in the paper. So, but it's still in an archive paper, so I'm pretty sure they'll probably make these things better. So yeah, that's my presentation. If you guys have any questions, happy to answer them.
I have a question. Did
Sure,
they actually release their data